So we can go ahead and introduce yourselves to the speakers of the day. We are very lucky and have the pleasure of receiving Juan Ulloa, Juan Cañas, and Maria Paula Toro. They are coming from the Instituto de Investigación de Recursos Biológicos Alexander von Humboldt in Colombia. And what brings these three incredible people together today is not only the fact that they are playing a pivotal role in applying and pushing the use of passive acoustic monitoring for conservation applications in Colombia. It's also the fact that they are, of course, amazing human beings, because I've been lucky to work and have got to know them for a couple of years now. But they are also the grantees of the GEO, which is the Group on Earth Observations, Microsoft Planetary Computer Program. And today they were kind enough to be here and share with us the takeaways from this undertaking in this project. So Juan and Maria, thank you a lot for joining us today, and please take it away from here.
Thank you so much, Ben and Larissa, for opening this fantastic space to all of us, and a very special greeting to all the colleagues who are connected for this talk. So this talk is going to be collaborative and transdisciplinary. With me, you'll have Juan Sebastián Cañas, an applied mathematician passionate about artificial intelligence for social impact in biodiversity conservation. Maria Paula Toro, a biologist with a keen interest in behavioral and evolutionary ecology of amphibians, focusing on animal communication and the impact of the environment on behavior and adaptation. And I'm a scientist, Juan Sebastián Ulloa, that navigates between the realms of ecology and engineering, and my research focuses on developing intelligent tools, aid monitoring, and comprehending trends in biodiversity. As Larissa said, we all work at the Humboldt Institute, which is an institution established in 1995 in Bogota, and we develop research that contributes to the knowledge, conservation, and sustainable use of biodiversity. We also want to acknowledge all, because we're part of a larger team, so acknowledge Diego, Larissa, Rogerio, Masao, Vinicius, Breiner, Jorge, Hernan, Luisa, and of course, all the team that's behind the SoundClean Research Network and the institution that made our research possible. So when we think about machine learning and bioacoustic, passive acoustic monitoring, maybe this is the image that came into our mind. So to have a device, can be a cell phone, it can be an audio recorder that is capable of listening to a clip of audio and name all the species in just a few seconds. And I think that's where we all want to get. But the truth is that there are many other applications of machine learning for passive acoustic monitoring. But before going there, let's start with a simple definition of machine learning, which is a definition that I like above. There are many definitions from Arthur Samuel, which says that machine learning is a field of study that gives the computers the ability to learn without being explicitly programmed, because this makes the emphasis that there's a change of paradigm. So machine learning is a subfield of artificial intelligence, and then you, inside machine learning, you would have deep learning, which is very trending right now. The change of paradigm is that goes from the hard code specific function, so trying to imagine all the possible outcomes and thinking about what can you answer to all these possible outcomes. And the other approach is trained by example. That means you build an architecture and you give example, and this architecture can adapt to map the inputs with the outputs. So let's give a little bit of example on this, because machine learning, you can divide it in two big fields, which is supervised learning, where you want to develop models to find correlation between data labels and patterns within the data. And you have unsupervised learning, where you want to develop models to mine correlation within on-level data. The big difference here is that in unsupervised learning, you don't have labeled data. So you can do lots of different stuff. Maybe the most common one is identifying species by sound, which would be the problem of classification. But for doing that, for example, you can do transfer learning, which is using pre-trained models on other tasks with larger data sets that you can adapt to your own problem. You can use active learning, where you want to train models with few meaningful examples with human on the loop. Or you can also use regression to, for example, estimate population density from acoustics. And you can also use some unsupervised learning technique to, for example, do dimensionality reduction. So you can visualize and measure diversity between samples. You can use self-supervised learning for audio source separation. And you can also use clustering to estimate sound type diversity. All these are exciting opportunities that machine learning brings to passive acoustic monitoring. And it would be very nice to explore all of them. But in fact, we want to focus on something that's behind all these developments and which are essential. And this is the data sets, because the development of machine learning depends on the availability of data sets. This has been very evident when we go from more simple or shallower models to deeper neural network models, where you can improve the model performance on classification, but with the cost of having much more amount of labeled data. Because data sets are the building blocks of machine learning. What are data sets? It's just a structured collection of data for training, evaluating, and testing machine learning models, basically to develop them. A very popular data set is ImageNet. This comes from the field of computer vision, which, for example, has 1.28 million images, 1,000 categories, and was launched in 2009. I put some numbers here to see the huge impact that this data set has had in science. So more than 22,000 paper citations and 202 patent citations. And once you have data sets, you can build a benchmark. It's just the combination of a data set and a machine learning task. And this allows us to have a common base to compare the performance of different models. Unfortunately, benchmark and data sets have been quite scarce in passive acoustic monitoring. They have been focused on bird vocalization and temperate regions. And sometimes you can find data set that they like an evaluation metric, experimental protocol, or baseline. And all this, it becomes difficult to compare the models and the techniques to determine the most effective methods. We have a huge amount of methods that are coming out every day, but we're not sure which one works best for our data. So our objective is to provide an overview of the challenges and opportunities associated with developing fundamental machine learning tools, specifically data sets and benchmark in the context of passive acoustic monitoring. And to do so, we are going to work with these amazing little creatures, which are frogs and toads, whose vocalization are prominent component of the soundscape in tropical environments. They are the most endangered vertebrate group, with more 40% of the species considered at risk of extinction. And you have males during the breeding season that call to attract females, maintain territories, and deter competitors. The calling performance is tightly associated with individual fitness, and their status can be sharply tracked using passive acoustic sensors. And this is why we built in 2019 a collaborative program for monitoring tropical amphibians that's called SoundClean. It aggregates more than 40 researchers around Brazil, French Guiana, Colombia, and Bolivia. We have 38 monitoring sites and more than 45 100,000 hours of audio collected. And here we have a very common problem that most of you, I think you are here because of this. We have terabytes of audio recording, but we have this huge bottleneck that prevents us from getting ecological insight from our data to analyze all this data efficiently. So to analyze our data, we build this machine learning system where you begin this, of course, with data collection, and then you have to take a subset of this data to annotate it carefully by experts. Once you have the annotation, you can prepare a data set, and with that data set, you can train different models and have a benchmark. You iterate multiple times, and once you're happy with one of the results, you can make inferences on new data. So this is the overview of the machine learning system, and we're going to see right now the different steps. So the first step is the annotation procedure. Go ahead, Maria Paula.
So hello, everyone. I'm going to start from here, and I want you to picture yourself when you have already have a huge amount of data in your server, and you want to prepare your data set for machine learning. But how should be a data set be? Which are the features to be considered at the moment when you want to prepare your data set? So let's see. First, your data set should be representativeness. So you have to have in your data set the species sounds in a wide range of acoustic contexts. Your data set should be variety and diversity. You should include both species, those that are super common and those that are super rare, in different seasons, different hours of the day. And you should also have enough recordings that cover all this variation in the vocalization of the species that you want to include in your data set. And if you see these three first characteristics for a data set arise since data collection. So I want to highlight that here we are not talking about, in fact, data collection, but since there you are preparing your data set. Very well experiment designs led us to create a well done data set. Another characteristics are labels. Labels is add the information that you need to train your model. In our case, for example, we need to put the name of the species of each call to each of the recordings. And we need that those labels are consistent and from high quality. This is so important because the model performance is based on the quality and consistency of those labels. An inaccurate or inconsistent or poor quality errors in the models or a biased model, and that makes inaccurate predictions. But we are here with 45,000 of hours of audio, and we need to extract those recordings that cover those characteristics. And how we can obtain that? We can do that through the annotation data. The annotation data is that subset of recordings where you can annotate the audio files, train the models, and validate the models of machine learning. And at this point, we are here, and we need that this annotation data have a very good size, it's representative, and be variety and diversity. So for our case, in the sampling data, we have recordings of 1 minute each 15 minutes for almost 2 years. So where we start? So we have to take into account the experimental design of our data collection, and the natural traits of our study group. So with all the characteristics that we need to include in that data. With that, we ensure that the annotation data from each of the monitoring sites it's well represented. So here we have traits like daily periods, local breeding season, seasonal period, nighttime. And when you have select of this data, you can start your annotation process, start the labeling process. So the first step for that is establish an annotation protocol. This is a guideline that standardizes this process and ensure to maintain the consistency in the labels. And this is especially important when your data collection is extensive, it's collaborative, you have a lot of researchers working in the same data, and maybe different annotators and different labeling tasks. These protocols are very meaningful resource because they provide all the examples for annotations. They provide also feedback session with all the annotation, and they are built for a specific task for machine learning. In our case, is build automated tools for determining the species recorded with PAM. But here is the first question: how should we label? In the annotation process, we can find weak labels and strong labels. Weak labels are those labels that we can do faster, but they are less accurate. And strong labels are those labels that are more accurate, but are more time consuming. So which one we should use? For our case, for example, a weak label can be just the present absence of anuran species in 1 minute of audio file. And the strong label will be detect and select the temporal limits of this code at the species ID and the quality of their record signal. So here we find a very good opportunity in labels, to do labels. For example, you can also have here, just in this recording, there is a species A, B, and C, but you don't know where it is. And with a strong label will be, this is the species A, and this is the species B. The species A has a good quality, and the species B may be in poor quality. That will be an example of weak and strong labels. Here we found, we identify a big opportunity of working within a network. We have a network of experts, herpetologists, or bioacoustics for each of the monitoring sites that are experts and knows very well all these populations on all the community of each site. So this, the community of amphibian of this site, but these researchers have no time to make a detailed, strong label. But with their experience, they can provide, for example, a reduced list of potential species that let us reduce the possibilities of which are the species there. Also, they can provide weak labels just in the terms of presence, absence, or calling activity. So we identify this as a big opportunity because with that and with the cooperation, we can obtain a reduced and accurate list of potential species from each site and a general overview of the presence, absence of calling activity of the species. And also, if these experts provide a sonotype for species reference that can be used for another trained annotator, we can do the strong labels with a person that is perfectly trained. So with already our strong, weak labels, we can start the strong labeling. In our annotation protocol, we include 3 main elements to include in this labeling that are annotation codes, quality criteria, and selection of the codes. First, the annotation code, it's a unique code for each species and will help us to avoid typing errors and simplify the information to add from each species. And to create that species, we use the scientific name of the species. And second, we conduct detailed and visual and aural inspection of the spectrograms. And we here identify the temporal limits. This is the beginning and the end of the audio segments that contains the advertisement call of the species in the recordings. To facilitate the annotation procedure, we don't annotate every vocalization. Instead, we use a series of we annotate sounds events as a series of vocalization of a single species. This is when vocalization or calls are separate for less than 1 second. We just add 1 label and select this in just 1 label. But if the time between the vocalizations are longer than 1 second, we just split the label and annotate them in a separate way. So for example, a 10-second recording selection would look like this for 2 species. These are the codes. But in the tropical environment, the things are a bit more complicated. One of the major challenges at the moment to annotate recordings in the tropical environments are due to the levels of calling activities. In tropical environments, you can find a regular recording in which you can easily detect and identify the pattern of a call species. So here you can hear. You can easily detect and identify that species. But you can also find the formation of choruses in which the calls of the species can be of in which you can find that the calls of the species can be overlapped, but you can still detecting and identifying the species. For example, in the recording that you are listening, there are almost 8 species calling simultaneously in 10 seconds. Juan, you can stop now. And also you can find more challenges recordings that are those dense chorus recordings in which you can find highly overlap species callings and many species calling at the same time. This difficult in many ways the detection and the identification of those species in those types of recordings, but this is very common on the tropics due to the natural history of the neotropical anurans, in which, for example, explosive breeding when many frogs get out to reproduce in just one night. So here you can hear how. Yes. So to include all this variation of the acoustic context on the model, we additionally to the code and to the selection, the temporal selection, we include a quality criteria. This quality criteria was made according to the perceived quality of the call, and it was represented as high, medium, or low quality. A high quality is a call that is easily identified in the oscillogram, and you can visualize all the characteristics of that call in the spectrogram, and it's not overlap. A medium quality is a signal that is overlapped, but you can still detecting the acoustic pattern in the spectrogram and also in the oscillogram. And a low quality signal is that one that is highly overlapped and you cannot detect them in the oscillogram and can be perceived acoustically as far. So at this point of the annotation procedure, just 1 minute of recording label could look like this. So this annotation could last between 7 or 10 minutes for just 1 minute recording, but also depends from the chorus. If you have a chorus or a dense chorus, you can even last 20 minutes just for 1 recording. So for our sound claim data, we successfully annotate 4 sites according to our protocol. After all, the annotation, we highlight the important to ask the annotators about the process. And we encourage to provide reports that allows to track the data, and the most important, provide reference labels to future annotator. With that, we have finished for the annotation process, and you have, for example, an output like this, when you have the beginning of the call, the end of the call, and the species and quality associated to that call. And here we have learned that protocols are essential to develop data sets. Local annotator expertise are key to identification tasks, and there's a need to develop protocols for tropical environments. And this is the primary resource to complete our data set. So I let Juan Cañas to continue.
Thank you, Maria. Now we are going to our machine learning system again. After the data collection and annotation part, we are going to start the dataset preparation and the benchmark design. So we start building an audio dataset for machine learning. As you know, the input of a machine learning models are not the 60 seconds audio recordings. So we have as an input the 60 seconds audio recordings, and we frame the species identification problem as a multi-label classification task. Why we did that? Because we need to consider the high overlapping between calls, and we apply a set of transformations over the raw audio files and annotations to obtain a dataset suitable for use with the machine learning models. We apply a 1 second sliding window of size of 3 seconds, and as an output, we have a samples of 3 seconds. What we obtain is the anuran set, a dataset composed of 2 biomes, 2 regions in Brazil, 4 sites, 42 species, 26 hours of annotations, and more than 93,000 samples. Other attributes of our dataset are the dataset comes from a biodiversity hotspot. This is very important considering the bias towards wealthy countries in machine learning. So we have a problem, and we need to increase the representation of datasets from the neotropics, and with the anuran set we obtain that. Other characteristics are the strong and weak labels. We can start to explore questions about strong and weak labels. And another characteristic is that we have a long-tailed distribution. This is a very common situation in machine learning when we have a very few classes with a lot of samples, but a lot of classes with very few samples. And it's not only common in machine learning, but also common in ecology. There are a diversity index like Shannon index, where these long-tailed distributions are common situations. We opened this data set, and currently there is a link in Zenodo, so you can start to explore your questions and your ideas using the Dataset. But we want to explore more about passive acoustic monitoring datasets, so we can check what is the Dataset in context. There are a lot of works in ornithology and bat passive acoustic monitoring. We have a lot of datasets, but currently in the audio area, previous to machine learning, there are a lot of research in speech recognition, in environmental sound. This is not an exhaustive list of audio datasets, but we need to compare what we are doing in PAN. Paradoxically, what we see is that in PAN we are collecting terabytes, but we are not opening the data that we are collecting. There are also problems and limitations in terms of hardware and storage capacity. But if we want to use these big scale models, we need to increase the representation per taxa, and we have to do a lot of things as a community to increase the representations of our datasets. After this dataset, we are going to work in a benchmark experiment. The idea of the benchmark is to create a basic way to compare with other models, machine learning. So we start with a very precise question, that is the question of a species co-identification framed as a multi-label classification task. After that, we choose the performance metric of F1 score, and we split data set using the iterative stratification using the audio files of 60 seconds to avoid any poisoning between the training and the testing set. We use a very basic baseline, a very standard baseline, that is, we use as an input the audio recordings. After that, we change the audio to an image in the form of a spectrogram and apply a set of augmentations and use a ResNet pretrained in ImageNet. This is an idea from an area of deep learning called transfer learning. So we start with this big data set called ImageNet that we talk in the first part of the presentation. We train the first part of the neuronal network. We train the weights, and we use that weight for our problem and use a final custom layer tuning in our data set. So in that way, we can use the knowledge representation of the first part for our problem and tuning for our species co-identification problem. What we obtain is that deep models performs better, but great classes are hard. If you remember the long tail distribution, we divide in rate classes, common classes, and frequent classes. So the frequent classes in deep models performs better, but we have a lot of work to do in the rate classes. So this is a benchmark that is opening to work in the community to advance in these rate classes problems, because as you see, the performance in F1 score is still very low. We can see in detail in the four sides of our study, and what we see in this plot is the samples of each species and also the performance. What we see is that all sites have a positive dependence in size and performance. There is a positive relation in almost all cases, and we need at least 1,000 samples for an accepted performance. And there is a caution messages, that is that we cannot use all the species for ecological inference. We cannot use machine learning with blind faith, so we select our best models and the species that have a good result. And with that species, we come back to our machine learning system, to the last part of our machine learning system, and we can start to create inferences. The last part of our project is to create ecological inferences using the models that we trained. So we use all the sound clip data in 4 sites. We apply our best performance model or our sound clip data. This data is basically 1,700 days of study, 150,000 audio files, and more than 8 million of detections over these files. And what we obtain? What we obtain is that PAM powered with machine learning provides new lengths to ecological inferences. What we see is the model confidence of present in 15 minutes each day across 1 year of assessment. This is the acoustic activity of 40 species with bigger resolution never had before. As you can see, we have very detailed information of the species activity, and we can start to asking questions about acoustic activity and the acoustic space between species. Other question that we can start to ask is the question of what is the relation between changes in species activity and temperature? So this is a question related with climate change, and we can start to correlate the time series of species activity and temperature. So I know that my ecologist friends have a lot of questions to do with that data and with our machine learning models. And we have in this moment a big opportunity to start exploring these new questions using these big models and the data sets, and also the passive acoustic monitoring data. But for our friends in machine learning, there are also very interesting news. We see PAN as a playground to explore machine learning questions. This is like a symbiotic relationship. We want ecological inference in the science community of ecology, but we also have theoretical questions in machine learning that can be explored in using data from passive acoustic monitoring. One of these questions is our basic question is the fine-grained audio classification problem, is how to classify a species call in natural environments with co-occurrences between species and other taxons in noisy data. Other question is in the interface of human machine collaboration, is how to optimize the annotation expert time. Manual data processing does not scale, so we need to search for new ways to explore the annotation process. Another question is the self-supervised learning question, is how to use the big amount of data collected without intensive human intervention in machine learning models. Questions around few-shot learning, how to improve performance with small samples classes as for species. And my favorite question is the domain shift question, is how to generalize the inferences in new sites and new seasons. We are going to explore one example of this question, and it's the question of geospatial distribution shift. This is an ubiquitous problem in machine learning, and it's the problem of how to detect species calls in a new site if I have a model trained using previous sites. This is a translation of a question of machine learning, but in terms of passive acoustic monitoring, and it's an ecologist zero data. An example is that I have a machine learning model trained in these 3 sites, and I want a model, and using these 3 sites, I want to infer the species in a new site. This is the out of distribution site or the test site. And what we obtain? We did a set of experiments, and what we obtained is two kinds of shifts. The first shift is the biome shift. We have the same species, different biome and site. We use the training data from Cerrado. We test in distribution with Cerrado, and we obtain a performance. But when we test out of distribution in other biome, we see a declining in performance. The second type of shift is the site shift, same species and biome, but different site. What we obtain is that in that case, the distributions also falling down, but in but less critic than in the first biome shift. And our hypothesis is that soundscapes can influence machine learning models. So this is a very interesting part of our exploration of geospatial distribution shift in passive acoustic monitoring, and is one of the examples that using a passive acoustic monitoring, we can start to play with machine learning questions.
Thank you very much, Juan. So let's wrap up. So we've seen how we can build a collaborative data collection, which you have to subsample in a way to get some representative samples to annotate carefully by experts. Once you have this annotation, you can build a data set. And with this data set, you can train models and iterate multiple times. Once you're happy, you can make new inferences. During this process, we've seen several challenges for open challenges in tropical acoustic environments. There are high diversity of signals, of course. We found also dense choruses where you have masking signals with co-occurrence of multiple species. So this is a multi-label scenario. You have also the problem of distribution shift and poor generalization. And we have this huge problem of long-tail distribution. But most of all, we have a limited interdisciplinary capacity between machine learning and ecology. And what we want to say is that the technology to develop the models capable of analyzing or recording is just around the corner. However, a fundamental requirement is still lacking: data sets and training for training larger models and validating them. Constructing a diverse representative data set that captures the vast acoustic diversity present in tropical habitats may initially appear overwhelming. Nonetheless, most of you are already making manual annotations, but unfortunately, most of the time, these annotations remain in text or CSV files on the lab. Scaling up the annotation task is relatively straightforward with standardized protocols. The potential benefits of pooling our efforts are immense. The machine learning community has shown ever-growing interest in tackling biodiversity data challenges, and complex soundscapes provide an exciting opportunity to develop creative solutions. In other words, PAM offers a setting for both exploring machine learning questions and crucial application in biodiversity conservation. Our invitation is to work together on this challenge, sharing knowledge, sharing data to promote ecology and conservation at a critical time for biodiversity. Thank you very, very much.
Thank you, everyone. Once, Maria Paula, thank you a lot for this very enlightening presentation. If you agree, we could take the next minutes to take some questions. Yeah, so if anyone wants to chime in and open their microphone and ask any question directly to the speakers, please feel free to do so.
One question that I've seen, thank you all for that talk. It's was so clear, and yeah, it's just great, this community that you're building and these standards that you're putting into practice. Several people in the chat were wondering if this annotation protocol is available. So could you let us know if we can find this protocol and use it in our work?
Yes, in fact, we want to make it available. So for now, we are polishing the annotation protocol because recently we've been having more and more people working on the annotation process. So this allows us to improve it. And once we have this improved version, the idea is to share it with everyone through the institutional channels at the Humboldt Institute. We have to think about the language because I'm not sure if we can publish in Spanish and English here at the Humboldt Institute, but I think we won't have any trouble with that.
Cool, awesome. I have compiled some
Great,
questions
thank you.
that people drop at the chat, but I also wanted to give the chance for those that wanted to ask directly, such as Tiago.
All right, let me go then. Great talk, guys, great talk, really, really interesting. Let me mention first, I have a question for Juan Cañas. Just want to mention first that we here at the DFKI in Germany are working on some tools for annotating passive acoustic monitoring data sets. We have one demo coming out at each KAI, an AI conference, called a human in the loop tool for annotating PAM data sets. That is work in progress. I will certainly share the news once we have something more mature, but let me get to my question. Juan, the question about the domain shift, which is a super interesting one. It's very cool that you guys have this data set to do the comparisons. You can see what you're seeing. I'm just wondering, do you know anything about when does the model fail when you look at a different biome or a different site? What is is there anything you can put in words about what is shifting in these domains? Does it make sense what I'm asking? You understand what I mean?
That's a very big question because it's a question of why is happening that. Our hypotheses are that there are like spurious correlations that are associated with the machine learning models. For example, the soundscape associated with that, or the species around the species of interest. For example, there could be other insects that are associated with that, with the presence of an anuran. So there could be different possibilities, and currently we are exploring what is happening behind this shift, but we don't have in that moment a very strong answer. But as you say, this is a very big question, and it's an ubiquitous problem in machine learning that happening in camera traps, in satellite imagery, and there currently a benchmark called WILDS that is a benchmark of distribution shift. So this is a big problem, but we are starting to explore that with passive acoustic monitoring.
Very cool, thank you.
Juan, since you're there were some questions in the chat that I think that would be awesome for you. For instance, Namitsa Suresh has asked, have you been able to compare the performance for pre-trained ResNet with a model trained from scratch? Just curious about the efficiencies.
Juan Cañas, can you answer that?
Yes, in the first part of our project, maybe 1 year ago, we started exploring basic models using gradient boosting regression classifiers, support vector machines with a set of features, and we started a model from scratch using a convolutional neuronal network. But what we see is that if we have a lot of array classes with a small number of samples, what we obtain is that we increase the performance with the pre-trained ResNet. So in that way, we decide to use this architecture of the ResNet as it is very common and is very used in almost all benchmarks. So we did that. We did that experiment, but what we obtained is that ResNet and transfer learning performs better than convolutional neural networks from scratch.
So sorry, just as a follow-up to that, do you have an idea of why that would be the case? Like, is it the size of data available? Like, would you expect better performance if you, with a model trained from scratch, if you had more data versus the ResNet pre-trained on ImageNet?
I think that the main point is that in the first part of the layers of the neural network are trained using a big data set that is ImageNet. And the neural network use this well representation and this and the way of learning the features are maybe more diverse, more efficient, because you have a lot of data, and deep learning you need to use these big databases to start to have a good representation, and also to train a matrix of weights to have a good representation. So in the first part of the neural network, you use this good representation, and after that, in the last part of the layers, you tune this representation with your data. So basically, the idea is that you need to scale with these big data sets, and maybe if we as a community construct a big data set as an ImageNet, but using passive acoustic monitoring, we can improve the performance using these pre-trained weights in our dataset only for audio.
Yes, and just to complement that is that that's why we want to publish this data set, so you can try all these interesting, really cool questions, ask them to this data set, and begin to understand how to build better tools for passive acoustic monitoring. And I think that's what we're really, really missing here, is to have this big data set. And instead, it's quite crazy that we use pre-trained models from image, because we don't have good data sets for environmental sounds. Or I think we might have to try it right now, but or using passive acoustic monitoring specifically. I think that should work much better, but we have to first build this large data set.
Okay, thank you.
Still in this line, we have a question from Tiago Bicudo. How can we increase model performance when talking about CNN by making labels in xeno-counter recordings, since they are species-specific recordings with poor presence of background species?
Juan Cañas, can you answer that?
Let me see how to use xeno-canto for training the models. I think that the main problem is to have like strong labels. That is a very human intensive process. If you have the strong labels, we can start to create like a big data set and using as a training set of the species that you want. The problem is that I think that in this moment, our species are like rare species, and we don't have like a set of species from other libraries. And currently there is an opportunity to use data from phonotecas or audio libraries using this data from the species. But using xeno-canto, using the strong labels is perfectly fine to using the training set if you are interested in some species of the xeno-canto community.
Yes, and just also to complement, maybe if I understood well, yes, we want to use some audio libraries, sounds from audio libraries, and the problem is that you have this mismatch between what we have in passive acoustic monitoring and what we have in these audio libraries, because the signal to noise ratio tends to be really good. And I think we have to find a way to some sort of data augmentation to add some noise that we can use at best this data that's in sound libraries. And that's also a step that we're taking right now.
Awesome. I appreciate it, guys, the answers. And since we're reaching out the time, I wanted to re-ask the question that was asked by Laura. How did you manage the cooperative work with peers at different physical locations? I mean, how was the data annotation and sharing process? Did you use some kind of cluster, or everyone was just working locally?
Okay, I think you can also answer that question, Larissa, because Larissa has been helping us a lot. She's also part of the network and like coordinating with all these researchers, so they give us this annotation. And at the beginning, of course, we wanted to have like a platform where we can all share the data, see the annotation, and that would be fantastic. But since we don't have that, because we want an open platform and everything, and we could not find that really, that we can upload the data, download data whenever we want, download the annotations, etc., etc. So we decided just to, yes, everyone can work locally with their data, and they just provide, for example, the CSV files with the wig labels. And once we have these wig labels, that's what Maria Paula showed us, we can start with other experts that are hired specifically to annotate the data, this more specifically annotation procedure to have the strong label. So to make it a short answer, we have a lot of work by mail to make this huge network work efficiently. So we are all aligned with the same protocols. The protocols have been essential. And yes, everyone works on their data, and we receive that data, and we try to analyze, make the strong labels more centrally for now. But the idea is also to begin to have some people on the local sites to make more strong labels now that we have this protocol much better. I don't know if you want to add something else, Larry.
One curiosity would be that when we start the project, well, some few months after starting the project, it was the pandemics. So it also kind of helped to keep people somehow connected, even if it was virtually. We've set some workshops that everyone attended to, virtually, of course, and had a lot of one-on-one meetings to talk about the manual annotation protocols. We shared a lot of screens. So it's an interesting thing that it also helped, like the culture of enabling the virtual and the online context, facilitate the connection, the physical connections between people. All right, we have some other questions here at the chat, but I strongly suggest that people can reach out to Juan Ulloa and Juan Sebastián and Maria Paula through their emails. If they all agree, we're going to upload this video or this presentation in YouTube as well, in our BioacousTalks page. And
yeah, sure.
Wow, awesome, thanks. Well, and then what our next presentation, we're actually postponing our next BioacousTalks presentation. So in 2 weeks, we are not going to see yourselves here, and we'll send more a detailed email as follow-up to the next set of presentations we're going to have in August. So thank you all once again for being here today. It was a pleasure meeting you all, and see you in a while.
Thanks again, you three, and great to see everybody.